So we're still working on the uncracked section, and we have this example, if you guys recall example 1.3. The question here is to determine the cracking moment, and the cracking moment is going to be that moment at which, if you apply it to the beam is going to crack at the bottom, at the tension side. Concrete strength was given as 4,000 psi. And it says here, use the internal couple method to check using the flexure formula. So we know stress distribution is going to be as shown, is going to be triangular shape. And definitely in the bottom is going to be larger than value than the top. Your reason is because neutral axis is going to be shifted up and you have here symmetry. So the distance from the top flange to the neutral axis is going to be smaller than distance from the neutral axis to the bottom flange. So I'm expecting the stress here is going to be larger than the stress there. Now stress distribution, we said if we're going to set this to be equal to the cracking stress is a 7.5 square root of F prime C as given by this equation. Which is the 474. So if you said the stress here is going to be 474, question is how much is the stress at this point? Now in this case, I don't really need to do the equation M over I times Y or times C. I don't really need this because I know the centroid or the neutral axis of the uncracked section, and I should be able to expect the stress here if I know the stress at the bottom. And I set it here again to the limit, to the cracking stress. Now, once you know the stress distribution, you should be able to find out the forces. The force here for the tension force is going to be simple because you have the stress at the bottom, multiplied by this depth from here to there, 15.33 divided by 2. Let's give you the area of this triangle. Now you do this integration on the width of the beam. And with that, you're just going to take this area here, multiplied by 5, as if you're trying to figure out the volume of this stress block. That's exactly what you do. Now, when it comes to the stress distribution, the compression zone, you're going to see here that we really need to split it into few areas or few volumes. Because on this T, you really have trapezoidal distribution. So this is why I added this line. Here's a flange, 4 inch, 20 inch for the depth. Stress distribution. It's going to be very tough to take the stress distribution and make it in one number to figure out the compression force. So I'm going to say, let me split it here into 3 volumes. The first one is going to be this rectangular shape, and this is going to be applied on the flange for the entire width of the flange. Second one is going to be this triangular shape applied also on the flange. So this trapezoidal shape, I'm going to split it into a rectangle and a triangle. Now for this little compression on the web, I can do it as just one triangle. So, okay, now I need the 3 forces, C1, C2, and C3. And for each one of them, I need to figure out distance from the tension force to the compression force. So this is going to be Z1, Z2, and Z3. I put here all the numbers that you need. I put the 867, depth to the neutral axis, 1533, neutral axis at the bottom. And then I said this is going to be at 1/3 from the bottom. You take here 1533 divided by 3, give you the location of this point load. And for that, the distance from here to here is going to be 10.22 inches. And for the 3 small forces, I said, well, where is the point of application? For example, C1 is going to be right at the mid-height of this rectangle. That mid-height means that you're going to have 2 inches above, 2 inches below this point of application. For C2, it's going to be at 1/3 of this triangular height from the top. As you see here, this is going to be 4 inches divided by 3 is going to be 4/3. 2/3 of the 4 inch is going to be 8/3. That's why I have this 8/3 from here to there. For this triangle, for C3, it's going to be also at 1/3 of this base from the top. So it's going to be 4.67 divided by 3. This distance from here to there is 4.67. It's going to be 1/3 of it, and this is going to be 2/3 of it. Now the question is, how would you find out Z1, for example? Z1, you say, is going to be equal to this distance from here to there, and then you add the distance from here to that point. So you say 10.22 plus 467 plus 2 inches is written right there. After that, you say the moment is going to be equal to, now if you like to figure out the moment here, you take the moment about one of the points, as you guys learned in statics and structure analysis. If you like to find out the moment due to these forces, you need to take the moment about one of these points. And it says it's going to be equal to 0. Let's take the moment about this point, about this tension force point. So it's going to be C1 times Z1 plus C2 times Z2 plus C3 times Z3. Give me the internal moment. We said that this is going to be equal to the external applied moment. So that at the end, total moment applied at this section is going to be equal to 0. External is going to be equal to the internal moment. We don't know the external moment, and actually this is what we'd like to figure out. This is going to be called the cracking moment. So cracking moment equals, on the other side, is going to be C1 Z1 plus C2 Z2 plus C3 Z3. It's exactly what you have here. They split into 3 moments, and then they add it at the end to be the cracking moment. Any questions before we move forward? Is this a little bit more clear with this distribution that I just put there?
Yes.
And the values should be able to help you out with figuring out these forces. If I were you, just to start this problem from scratch, I'm going to start to solve it myself, cover all of these numbers, and then back check my numbers here once you develop this.
Sorry, Professor, do we have that slide?
For what? Say it again.
Do we have that slide, this one?
Oh yeah, I just posted. I want you to check it right now. Be sure that you have
Yeah, they're there. It's there. I have it open.
I just replaced the example with this one. So please be sure that you have it there.
Okay.
Let me know. If you cannot access it, let me know, please. All right. Now we're going to be moving to rectangular section. Now what's going to happen after cracking? This is going to be the question. What's going to happen? Now we need to have the reinforcing. Reinforcing here needs to start to work with us. So the previous slide said it's going to be about uncracked concrete section. Now this slide said it's going to be about cracked, which means we call it here reinforced concrete. We don't really call it cracked because all concrete are expected to crack. And the reinforcing is going to be mitigating the crack and control it. So I don't want to say cracked and uncracked. I'm going to say uncracked. I'm going to say reinforced concrete. Uncracked is going to be before the cracking point, before you reach the tensile stresses to F sub CR. And reinforcing, it means you have more moment than the cracking moment. Okay. I'm going to be looking here at structural elements in standard, like typical building. You're going to have here, as it says, second floor, first floor. And then you have here a basement. This is going to be concrete slab on grade. This also is going to be concrete. You have a basement wall. It is called here foundation wall, but we usually call it in business, we call it basement wall. We have reinforced concrete slab. We call this the first floor. Then also reinforced concrete slab for the second floor. As you see here, that you may have joists running, small joists. It's not really beams. When you have it repeated, let's say at 2 feet or 3 feet or 4 feet in center, and you have plenty of them, we call this a joist. And this one here is what we call a beam. So a beam is not going to be repeated that often. It's going to be repeated, let's say, at maybe 20 feet or 10 feet or 30 feet, but it's not going to be like this. So this is going to be the difference between a joist and between a beam. As you see here, the beam and the concrete slab is going to be monolithic, which means it's going to be formed and poured in the same time. So this is here one piece. Whenever you have an opening in the concrete slab, you need to put a beam. You see this beam around an opening? You need it. So what happened? This thin concrete slab is supported by the joist. And then the joist is going to be taking the load and dump it to the beam. Beam is going to be taking it to the column. So now the column supports the entire level. Of course, it's not going to be just one column. It's going to be all of this column that you see and the wall. Now load is gonna be coming down through the first floor. You're gonna be taking the same load that you have on the first floor. You're gonna say supported by the slab. In this case, I don't see here joist, so this slab is gonna be supported by the beams. So the slab gives a load here to the beams. By its turn, is gonna give it to the column. Now a question. Do you think that the load is coming here from the top? Is it going to this slab, to the first floor slab? Or just bypassing it through the column? Because when I design the first floor slab, I need to know what loads I'm gonna be designing it for.
It's attached to the column because I see right where the column and spread footing are, there looks to be another beam.
So the question is, when I design the first floor slab, do you think any of the top level is gonna be supported by the first floor slab?
No.
No, nothing is supported by that, right? Which means the column load is just going continuously, right? All the way down. And each slab of this just supports itself. If I set this column section right here, does this support the second floor or the second floor and first floor? Right here. Can I say this section here? It's what?
Just the second floor.
Just the second floor. Very good. So I'm going to be taking it down here. How about this column? Does this support the first floor only or first floor and second floor?
First and second.
First and second.
First and second. So I'm going to say, okay, column load is going to be going all the way down to the footing. So this footing here supports the entire building because it supports this column and this column supports both levels. Does this make sense? So if you'd like to design the column at this level here, what you need to do is to figure out the load coming from the second floor only. If you like to design this column here, you need to take the loads coming from the second and the first. And when you design the footing, you need to take all the loads coming from the top. All right.
So Professor, is that how the Burj Khalifa is also supported with one big spread footing, well, with several distributing the weight, or would there be like a finite floor where it would then take the load?
Now what happened in this floor system, let's say, this is not the only column supporting the slab, right? On the top. We have other columns and some walls. So I'm gonna say this column here and this column, maybe another column in some other place. This load, which means the weight of this slab and the life load, like the occupancy load. When you have furniture and you have people walking on it, it's gonna be all supported by this wall and supported by this column, supported by this column. Distribution is gonna be based on the stiffness or tributary area, if you like. So for each one of these elements, you need to figure out how much load is gonna be going there. This is why we have statics and we have structure analysis that you guys have taken already, right? And then you're gonna keep track for each column. You can give, let's say, each column a number. You call this column C1, this gonna be C2, another one C4 and C5. You just give it the symbol that you like or the mark that you want it to. And for each column here, say from this level, you can do like a big schedule, like a spreadsheet. You say from this level, it says this much pounds or kips. Same thing for this column, same thing for this wall. And then you keep track of them. And then you say, right at the foundation, I have the loads coming for column. Let's say this is gonna be C1 coming from here and all places. Make sense? All right. Here's a different type of construction. I don't see here beams. So in here, I've seen beams. In here, I don't see here any beams. I see something here that we call here flat slab or flat plate, if you like. Here's flat slab, here's flat plate. I don't see any beams, but I just see a beam here at the back. And then I see here a wall. So a flat plate can have maybe a ridge beam, like marginal beam, something in the perimeter is gonna be accepted, and you still call it flat plate. Good thing about this system here that you don't see any beam dropping down. So if there is no full ceiling, like T-bar ceiling, it's gonna look beautiful, right? Because you don't see anything there. Unless you have pipelines or you have light fixture and you want it to be exposed. But if you have, let's say, a parking structure or exhibition hall or something that you don't want to see beams, this is gonna be a perfect solution for you because you don't want to show beams to people unless you'd like to show. It's gonna be a different story. So comparing this system to this system, there is no joist, there is no beams. This is what we call here flat plate. It's supported by column directly. The flat slab here, we don't call it flat slab because this one at the top, this one's gonna be at the bottom. This is not the reason. We call it here flat slab because for each column, we're gonna have this column capital. You see this column capital? We call it column cap. And also we have this drop panel. The reason we have this drop panel, and a drop panel just, is like a thickened slab. So the slab thickness here, let's say 10 inches, and here the drop is gonna be maybe 6 inches. Total thickness of the slab here is gonna be 16. Here, let's say it's gonna be 10 inches. Now I want you to think here about putting lots of loads here on the roof. Just put some loads and see what happens. This load wants to push this slab down and also wants to push this slab down. Now you have this potential that this column is going to be penetrating the slab, and we call this punching. So you don't want this column to punch through the slab. Otherwise, it's going to be like a mode of failure. It's going to be a collapse. You don't want to see this. So in some cases, if the slab is so thin, maybe you'd like to stiffen it by adding this drop panel or adding this column cap, which means at this connection between the column to the slab, you make the column larger. That's exactly what you do. So the punching interface between the column and the slab is going to be greater. And with that, you're going to make it safer. This is the reason behind it. So the reason that we have this column capital and drop panels is to control the punching shear. We call this punching, and since it's going to be like penetration or punching like this, it's going to be like a shear effect. It is not going to be like flexure, like a moment. It's not going to be like an axial load causing this punching. It's going to be a shear that causes this punching. And this is the reason that we call it punching shear. Same story about the load path. What is the load path? The load path is, we're talking here about the dead load and live load that go through the column, and then the column supporting all of the slabs goes all the way to the foundation. We have the same load path here. Load starts at the roof. You have the self weight of the slab, which we call here dead load, and we have the live load, the roof live load, supported by these columns. So the columns gonna be going here, the loads gonna be going to the column. You have more than one column. Distribution is gonna be based on how much each column is supporting. We call this tributary area. And then the load is going down. Also, the first floor is gonna be dumping some loads on these columns. And this column here, this column section supports both levels. At the end, it gives the force or the load to the foundation. Let's look here when we have a concrete slab and we have few beams. Let's look here in details about the load path. How the load moves from one point to another point. If you want to design the slab here, and we call this one-way slab. What is one-way slab? Just, we call this two-way slab or flat slab, if you like. So you can call here flat slab or two-way slab. This one here, we call it one-way slab. What's the difference between one-way slab and two-way slab? One-way slab, when you have the beams running parallel to each other, and the slab, this is gonna be a strip of the slab that I'm gonna be taken to use it in my analysis. It's gonna be supported on beams. So this slab here, it takes a load from this point. Let's say that you're gonna bring some point load and put it right there. Where is this point is going? You look here at the load path. You say this point here is gonna be dumping the load on each beam. So let's say if this right in the middle, this is gonna be P, you're gonna have P over 2 here and P over 2 here going to the beam. So when you look here at the load direction, load goes only in one direction. Some of the load goes here, some of the load go there. No load is gonna be coming this way or going this way. So the load direction is gonna be going to each beam. This is why we call it one-way slab. When you look at this system here, and you say, let me put some point load here in the middle. Let's say I'm gonna put here a heavy equipment on the rooftop, like an AC unit or whatever, right? How the load moving to the column? Is it gonna be going like to this column and the other column in the back and this column also? Is moving like in all directions, in two directions? Like some load is gonna be going this direction, some load is gonna be going to that direction? Or just it goes to some beams? I mean, I don't see here any beams. So the load is gonna be moving in both directions, if you like to call it X and Y. So it's gonna be moving, let's say here's the X direction, Y direction. Yes, the load is gonna be moving in two directions. While in this case, if you put here the equipment, the rooftop, it's gonna be just going only in one direction. Why would the load go this way and not to go that way? You say because you have some beams to support it. Here, you don't have here any beams at the edge. So how much load is gonna be going there and why it's gonna go there? If there is no support for this edge here, no way that the load wants to go that way. At the end, this load wants to go to these four columns. So the easiest way, shortest distance for this load to get transferred to these columns is just by going first to the closest support, to the slab, and then after that, go through the beam to each column. So I'm guessing again, what is the load path as a conclusion? Yes, a load path starts here from the middle, through the slab to both points. It goes here from point A to point B and C, right at the middle of each one of this beam. And then right from B is gonna be going to column E and column D, and here's gonna be going to column F and column G. Now we have an idea how the load moves from one point to another point. Any questions? Are we good?
Yes.
Excuse me, is there any other geometry ratio for just making the difference between one-way and two-way slab?
Yes, yes, Ramin. Where is your name, Ramin? All right, yes, but we're not there yet.
Okay.
For the one-way slab, I just want to explain here that the load is gonna be moving, usually it's gonna be in one direction. We have Christian Rios.
Yes.
All right. Let me mark you in. Carlos?
Yes, I'm here.
Carlos, okay. Great, I like this system. It's very handy. All right, thank you. All right, so now we have an idea about the load path when it comes to one-way slab. Here's when you have some beams. Now I'd like to understand what the beam design itself, because look at this. I'm looking here from a certain angle. I'm thinking here about the slab. How would I design the slab? The slab is gonna be this rectangular section. I know the slab is gonna be extended for many feet right and left, but if I like to do a reasonable design for the slab, gonna be taking a strip, let's say for the width of 1 foot only, and do the design on this. And then the rest of this strips right next to it is gonna be very similar, identical to this strip. So let's say I'm gonna come here, take this, design it, put this amount of reinforcing in there. So I'm gonna say whatever that you put in this foot, they just repeat it, because this is gonna be a good representation for the remainder of the slab. Okay, now how about the beam? Look at this section here and look at this one, just looking from that side, right? Or look from that side. If you look from that side, you're gonna see this L shape and T beam. Look at this, here's the L shape and this is gonna be the T beam. So the slab strip is gonna be running this direction because the slab is supported by these two continuous beams. Now looking at the beam, where is the beam section? Someone's gonna say beam section is gonna be like from here to there, is gonna be this section, the rectangular section. Someone else is gonna say, how about the slab itself? Why didn't you consider a section of the slab itself to be working with the beam and form the beam with you? Because someone else can say, is the beam is gonna be from here to here only? It's gonna be the depth of the beam. You guys remember the depth of the beam that we discussed? The edge, that we call total depth of the beam. Now, where's total depth of the beam? Is it from here, from this point to this point? There's gonna be the total from here, bottom of the beam, all the way to the top of the slab. Someone's gonna say, this is here poured monolithically, which means that they were poured in the same time. So it is gonna be unfair if you just say depth of the beam is gonna be all the way from this point to that point. I'd like to include the slab thickness here. So depth of the beam is gonna be from that point, top of the slab, all the way to the bottom of the slab. So, okay, good. How about the flange? Wouldn't you consider this part of the slab and this part of the slab to be acting with you? You say, why is the reason of this? I'm gonna say, because if the top is gonna be seeing here some compression, and you know that concrete is not perfect in compression, you know, it's gonna be very strong, but not good enough for the loads that we have in there. So I'm gonna say, why don't I add a little bit of flange and make it like a T-section? And the question is gonna be, how much width should I consider of this beam or of the slab? How much width should I consider here? It's gonna be like twice as much as this width, 3 times, 4 times. Certainly you'd like to include as much as you can because it's gonna help in your design, but doesn't work this way. The code has a say here, and the code says the width of this T is gonna be limited, and they're gonna give you some equations to figure out the width of the flange on the top. We're not there yet. I'm just trying here to open the ideas for you. This one here, we call it an L beam. It's true that it's called here T beam, but usually if you ask anyone, they're gonna say this like an L shape and it's gonna be T shape. So usually we call this T shape and we call this L shape. But when it comes to the code is gonna be treating him the same. So it's gonna say the width is gonna be equal to, they give you an equation. The same equation works here for T beam and for an L beam. All right, I'm looking here for the potential reinforcement that I'd like to put here for the concrete slab. I'm gonna say here's a rectangular section. This is the one that we are used to, this one that we have seen. And we say before cracking, you don't wanna really look at this AS. And AS, as you guys know, is gonna be the total cross-section areas of this reinforcement bars. So let's say if I have 3 number 9, and for number 9, cross-section area of 1 rebar, it's gonna be 1 square inches. I have 3 of them, it's gonna be 3 square inches. H is gonna be total depth. D is gonna be the depth from the compression fibers, top compression fibers, to the centroid of the rebars, not the top of the rebars, not the bottom of the rebars, to the center of the rebars. The reason, because the tension force is gonna be right at the center of the rebar. And they'd like to figure out the distance from the top compression to the center, which means the point of application of the tension force. So, okay, this is good. I've seen this, understand these parameters. Now let's look here at a T-beam. This is a T-beam because I have a flange. Thickness of the flange is used to be, the term or the symbol that we use for it is gonna be either H sub F or T sub F. Sometimes you see it as T sub S, like slab thickness. HF is okay for the flange thickness. Depth is gonna be the same, but look at the depth. Because we have 4 rebars, now the depth is gonna be right to the middle of all of these 4 rebars. Because when I do the analysis, for me, this is gonna be 1 tension force. I'm not gonna do here 4 tension forces. It's gonna be just 1 in the middle at the CG of this 4 bars. So in here, I have 3 rebars. It's gonna be 1 tension force. The location is gonna be right here. And here is gonna be right in the middle. This is why D here refers to the center of this 4 rebars. Width is gonna be the same. We call this B here. We call it BW for the web. But if you decide to call it B, it's gonna be okay. Doesn't hurt much. And H again is gonna be the total thickness or depth of the beam. Now I guess this explains when we're talking about this shape that I said, where is the depth of the beam is gonna be from here all the way to the top of the flange, top of the slab, like in here. So do not consider it to here. No, it's gonna be the total thing, the whole thing. I said, okay. I'm looking here for different type of beams. Someone's gonna be looking at this and say it's gonna be like inverted T. Is this the way you have it? You say, no, we need to talk about this. But if you assume that the compression is going to be on the top, tension is going to be here at AS, the depth is going to be from the top compression all the way to the tension force location. Edge, top, all the way to the bottom. So in all of the three cases, I have passive moment. Passive moment means that you have compression at the top and tension at the bottom. Your neutral axis is going to be almost here, somewhere here. So in this case, I call this what? I call this rectangular beam. It looks like a rectangular section. And here I'm going to say this looks like a T-beam. This is the way I say it. This one here, I'm going to say this is T, but inverted T. Now, when it comes to concrete design, not because it looks like a T, I'm going to call it a T. I'm going to have other parameters to decide for me. I'm going to say, let's say neutral axis is going to be right here. You see where I'm putting here the mouse? See where it's going to be at? Let's look here at the compression. Compression happened on a rectangular piece of the beam. So I'm going to call it here rectangular section. If I say neutral axis is going to be here, it means a T section is exposed to the compression. So I may call it T section. Now let me do here the neutral axis. Now you tell me, would you call this a T section or rectangular section? It depends on the compression force. Is the compression force on a T section or rectangular section? Say compression happens on a rectangular section. So I'm going to say this beam here is a rectangular section. It is not a T section. It doesn't matter what would you put the reinforcement through, because I know that this section here or this area is going to be all cracked. Neutral axis is going to be roughly here. It's going to be a little bit above the mid height of the beam. So I know for sure that this area is going to be cracked. No compression is going to be happening here. So I'm going to call this rectangular section. We're going to have more examples on this. This is just to open the idea and the topic. Okay. Here's a continuous T-beam that we're just looking at, which is right here. Now we start to add loads to it from the top. What happened when you add load on the top? This is not simply supported beam. This is a continuous beam, right? There is some continuity. This beam can be continuous to the next column and next column from both sides. Just say once you start here to add the load, what's going to happen? You're going to have tension at the bottom, compression at the top. But once you come here to the column, you're going to see that tension is going to be in the top, compression at the bottom. If you recall here the term positive moment and negative moment, so over here, you're going to have positive moment causing tension at the bottom, and here you're going to have negative moment and negative moment. How do you identify positive moment and negative moment? You say, look at the tension side. If the tension is going to be at the bottom of the beam, we call this positive moment. If the tension top of the beam, we call this negative moment. And look here at the expected. This is going to be based on the deforming shape. Here, you're going to have crack at the bottom. It's going to be positive. Crack in the top makes sense. It's going to be negative moment, negative moment. If you'd like to add some reinforcing, where should I add them? Reinforcement mainly is needed for the tension side of the beam. So in here, I'd like to add the reinforcing right here to take the tension force. And here, I'd like to add them on the top. I'd like to add them on the top. This is going to be the main purpose of adding some reinforcement. I said, okay, let me look here at these sections. Here is section AA. Where is the compression? It's going to say compression is going to be in the top. How about in section BB? Compression is going to be at the bottom. So usually, you're going to see here a line, which is the neutral axis. This is the reason that we have this line here. And this hatching means compression. So compression is going to be on the bottom. You see this? It says compression zone. Look at the first one here. The first section. Compression on the top. Now, where is the neutral axis shown in this case? You say it is shown to be within the flange only. I said, okay, this is fine. I'm not sure exactly where the neutral axis is going to happen because I have another option, which is this section here, and chose the neutral axis to be right here. And it says here section AA. It's not continuing reading. Let's just say neutral axis going to be here or neutral axis going to be there. Do you have any other options? I'd like to hear from you guys. I have the neutral axis to happen either in the flange or it's going to be in the web of the beam. Any other options? Yes, Ruth, go ahead.
No, I don't
Are
think
you
so.
sure? Because I'm thinking neutral axis can be right on the top, right on the bottom. Can this happen? Or no way? Anyone listening to me?
Yes. I'm gonna just take a guess and say no. You can't have a neutral axis above or at the bottom, right?
This,
I'm thinking of like a column, but even then.
no, you cannot have it here. You cannot have it there. It needs to be within the column itself.
Mm-hmm.
Can it happen to be right at the bottom of the flange? Right here. You say yes, it can happen. So I have 3 cases for the neutral axis location. I can have it in the flange, I can have it right at the bottom of the flange, or I can have it in the web, like in this case. Okay? I said, if it happened here, what does it mean? Do I have a T section or rectangular section? I said in the previous slide, look at the compression zone. Does it look like a T section or rectangular section? I'm gonna say, let me look here. This looks like a rectangular section, right? Compression is rectangular section because look at the hatching. So it says here rectangular compression zone. Look in this case here. Is the compression zone rectangular or T? You say it looks like a T. I said, okay, so here's the third option. If the neutral axis is happening right at the bottom of the flange, it's gonna be rectangular or T. It's gonna be right here. I don't see here a T. It's gonna be also rectangular section. So if the neutral axis is happening within the slab or right at the bottom of the slab, right there, it's gonna be a rectangular section. And if it happened through the web, it's gonna be a T section by definition. Okay, this for section A. How about for section B? Section B compression is gonna be at the bottom. This is not gonna be a T section. It looks like a T, I understand that. This is gonna be the whole section. But based on this definition for rectangular section and T section in concrete design, I'm gonna say, let me look here at the compression. The compression happens in the rectangular section, so I'm gonna call it here rectangular section in my design. Now let's look here at the main reinforcement as shown in these sections. And here, where is the main reinforcement? Let's say main reinforcement or tension reinforcement is gonna be where? It's gonna be at the bottom, right? How about in this section? It's gonna be at the bottom. Yeah, it says here tension reinforcement. How about here at section B? And also in this section, if you may call this B, it happens on the top. This is where the tension is gonna happen. So when you do your analysis, you need to understand the following, that we have T sections, rectangular section. It doesn't matter if this is gonna be a positive moment or a negative moment, but what matters when you have compression and the compression happens on a segment of the section, because it's gonna be an entire section, it's gonna be the segment of it. If the compression happened on a rectangular segment, you call it rectangular section. If not, you may call it T section, like in this case. Also, you need to understand that the main reinforcement is gonna be in the tension side. So I have here tension reinforcement. How about this reinforcement? You can call it compression reinforcement. So why do you have them? We can study this later. But would you add some reinforcement to compression? I'm gonna say yes. But is this the main reinforcement or this is gonna be the main reinforcement? I'm gonna say this is gonna be the main reinforcement. This is here the main reinforcement in this section. It's gonna be the main reinforcement in this section at this location. Questions? You're good?
Yeah.
All right. Now, here's some reinforcement. I'd like to see here an elevation of the beam with some reinforcement. So first I have the beam running across, then I have a column, I have some continuity, the beam is continuous, and this is gonna be the end of the beam. There is no beam in this side, so the beam starts here, right? And then the beam is also continuous here. If you do here structure analysis, and let me remind you with this, in statics or structure analysis, you see here the moment at this point most likely is gonna be equal to 0. Here I'm gonna have tension at the bottom. Here I'm gonna have tension at the top, right? Very similar to that shape. So right above the column, you're gonna see some tension in the midi span. We call this the midi span. It is right in the middle of the span. What is the span? The span is the distance from this point to that point. So I'm gonna say here's the tension, and here's gonna be the tension. And then it shows, you see what happened to the rebar? It is bent a little bit this way. In reality, it's not really bent. This is just to show you how it's gonna look like, but it's gonna be side. They're gonna be next to each other like this. But if you draw it this way, you're not showing that the rebars are spliced. What does it mean by spliced? It means like this. There's a lap splice between them. So I'm gonna say here, look at the splice. How did you pick the location of the splice? Is it on the tension side or compression side?
Compression side.
Yeah, in a reason. I mean, of course, you cannot have it in the tension side.
Because concrete works a lot better with compression, and once you apply the compression onto the splice, the steel is gonna give that tensile force, and therefore the reinforcement can take all that load.
So if you have the option here, would you put the splice in the tension side or compression side? Compression.
Compression still.
You'd like to put in compression, and then you'd like to avoid to splice the tension rebar. Why? Because like what I said here, where's the main reinforcement? I said this gonna be here. Main reinforcement, which means tension reinforcement is gonna be the main reinforcement. You don't want to splice it there unless you really have to. And there is means and method. There's some more analysis that you'd like. But if you have the choice, definitely splice the rebars in compression. Do not splice it in tension. This is gonna be the message out of this picture. We good? All right. Let's look here for the beam analysis, the beam section itself. Here's a rectangular beam. This is what we are going to be starting with. We don't want to start with T section. T section is going to be a little bit complex in analysis. So we need to start with the simplest section and the simplest reinforcement. This is going to be the first and simplest section that you can look at. Rectangular section, there is no T, nothing at all. There is no even slab, just for analysis, for sake of analysis. In reality, it is unlikely that you're going to see a section like this. It may happen from time to time, but usually you're going to see a slab on the top. Total depth of the beam is called H from here to there. The depth, D, top compression to the tension. AS, total cross-section area of the rebars. B is going to be the width of the beam. Any compression steel shown here? I say, well, no. Does mean that there is no compression steel. I'm going to say sometimes you have compression steel, but you just ignore it because it's going to be very minor reinforcement that you don't want to make it complex in your analysis. It's not really impacting the strength of the beam. So for this, I'm not going to show it. I'm not going to consider it. Okay. This beam here exposed to passive moment. Definition of passive moment, tension is going to be at the bottom and compression is going to be on the top. Okay. Let me draw here the strain distribution and the stress distribution. This is after cracking because we have done it before cracking. And you know what happened before the cracking point? The stress above and below works as if you have a homogeneous section. And the reinforcing bars were not acting there. They were not triggered yet. There's no real tension force in there. But look at what happened here. Now you have here cracking. So below this point, the concrete is cracked, and above this point, this is going to be the compression in the concrete. So neutral axis is going to be here. If you like to do something similar to this hatching, you could have just drawn here a line, horizontal line, and do hatching here. So this is gonna be compression, it's gonna be in tension. Now here's the strain distribution. It's gonna be like a straight line. Now, what's your expectation for this X distance? Depth of the, we call this depth of the neutral axis. Do you expect this to be lower than d over 2 or more than d over 2?
Lower the
Lower.
d over 2?
So this is gonna be here, right? It's gonna be in this side on the top. It's not gonna be at the bottom, right? So what is the lowest location of the neutral axis in a case like this? Say lowest location, what do you mean? I mean, let's say the total depth here is gonna be 24 inches. I'm just throwing here a number. If this is 24 inches and you start to load the beam, neutral axis is gonna be right where? You're gonna see neutral axis is gonna be right at 12 inches at the beginning, right? You start to apply loads, neutral axis is gonna be right at the mid height before cracking. It's before you start to crack the beam. Now you start to apply more loads, the beam is gonna crack and the crack is gonna start here from the bottom. So what happened to the total depth? It's gonna get reduced. Why reduced? I'm gonna say, it doesn't mean that H is gonna become smaller, it's gonna be becoming 20 inches. But what I'm saying is, because the bottom is gonna be cracking, the effective depth is gonna be here, let's say, it's gonna be dropped down. Instead of 24, it's gonna be, let's say, 20 inches. So the bottom few inches from here is gonna be cracked. So the effective section of the beam is gonna be right here on the top. So what happened in the neutral axis? Would the neutral axis goes up or is it gonna go down? Yes? Anyone here?
Goes up.
It's going to be going up because usually it will try to be right in the middle of or the mid height of the effective section. So if you start here 24 inches, now all of a sudden after cracking this becomes 20 inches, neutral axis is going to be at 10 inches from the top. It's going to be shifting up. It will never go down. So I'm expecting this neutral axis to be up there, right? It's going to be in the top half of the beam. So, okay, now I understand. Anyone recalls when do you think concrete is going to be failing? Anyone recalls something about ACI and concrete is going to fail at certain strain? Did we do this?
Isn't it like 10% of the compressive force?
No, no, I'm talking about the strain. Let me share this. The introduction. Materials. You guys recall this slide?
It's 0.03.
Yeah, so when do you think the concrete is going to fail? Concrete is going to fail when the strain is going to be reaching 0.03. It has nothing to do with the stress. The stress here is going to be, let's say, 5,000, 4,000, 3,000, but when it fails, it's going to be here. And what we care at this point is going to be the amount of strain that you have in the concrete, not the stress that you have in the concrete. So at this point, I don't really care about how much stress there at the failure point. But concrete is going to be considered to be failing once the strain reaches 0.003. Okay, is this helpful? I'm going to say absolutely. It means a strain here, maximum strain. What is the maximum strain according to ACI? I'm going to say here is going to be 0.003. Okay, now I know when the concrete is going to be failing. Is this in tension or compression? This is going to be the compression side, this is going to be the tension side. So this is actually going to be in compression. And this is stress and strain relationship that you're looking at. This is actually in compression. It says compressive strength. It is not in tension because in tension is going to be very weak. It's going to be failing at very small stress value. So I said, okay. So understand it's going to be compression. And here the stress is going to be almost equal to 0 at the neutral axis. And right below it, concrete is gonna be cracking. That's my understanding. So concrete here is gonna be nothing. It's not gonna be working with you. But when you look at the tension side, you're gonna see here concrete is gonna be still working with you up to maybe like 400 psi. Correct? Like F sub CR, the tensile strength of the concrete. So in a little bit of here, concrete is gonna be still working. And right below it, concrete is gonna be cracking. How about the steel? Would you see here any stress in the steel or any tension in the steel? I'm gonna say yes. The stress in the steel is gonna be called here epsilon S. Now, if I know that this is gonna be here 0.03, do you know here the depth X of the industrial axis? Say no, I don't know it yet. But this is gonna be one of the variables that I'd like to work on. If I know X, I know that this is gonna be 0.03. Can you figure out the strain at the steel level? Say yes, I can figure this out because I have two symmetrical triangles. These two triangles, they're gonna be similar to each other. If you have the strain here, divide by this X, right? It's gonna be equal to epsilon S divided by D minus X, which means this height. And with that, you're gonna be able to figure out the strain in the steel. Okay, good. So this is strain. They call the strain compatibility or strain problem. I should be able to solve it some way. I'm not trying to solve it now. I'm just trying here to open the parameters, ideas that we had. Numerical example is going to make it much easier for us. But first, we need to understand this strain distribution, why it happened this way. Now, let's look at the stress distribution. I'm going to be putting this here again because this is actually going to be very useful. Let's say that I'm working here with 4,000 psi concrete. So this is going to be the stress-strain relationship. Here is the stress, here is the strain. Out of this curve, if I give you this curve here, I'm going to say, how much would the concrete stress when the strain was equal to 0.001? I guess say 4,000, 0.001 is about 3,000. And say, okay, how about when the strain is equal to 0.02? Say 4,000. How about when the concrete equals to the strain is going to be 0.03, maybe 3,500 psi. When the strain in the concrete equals to 0.0005, like half here, we're going to say maybe 2.3, 2.4, okay? Which means this relationship that I have between the stress and strain is going to be very helpful to me to be able to develop the stress distribution that you're looking here at. How's that? If this is going to be here 0.03, how much is stress that you'd have here? Well, I was just talking about this. Let me put this back here. And say, look at this. I said, okay, when the strain equals to 0.03, I have the stress of about 3.5 ksi. So this point here is going to be 3.5 ksi. When the strain equals 0.002 is equal to 4 ksi. So in here, this is about 2.02, and this is going to be 4 ksi, the highest point. Which means this diagram that you're looking here at is going to be exact. I'm going to say here, diagram of the stress strain distribution. Just a copy of it. For each strain value, you have a stress value, and this is exactly what I've done from here. Can it be taken here, digitize it from each strain value here, just figure out the stress and then draw it here. Can someone tell me what is happening here? What is this? Can someone explain me what is going on here?
Is that the tension and compression?
Yeah, and how much is this? Do you know how much is this value from here to there? This point to that point? As a stress value?
10% off compression.
This is going to be the FCR, right? This is going to be the tensile strength of the concrete. Because right below this neutral axis, you're giving the tension side. Right above it, you're giving the compression side, correct? So I'm gonna say in this case, once you go here below this tension side, right, once you below here, the neutral axis, you're giving the tension side. And the maximum stress that the concrete is gonna be able to take is gonna be 7.5 square root of F prime C. So this is stress value here is gonna be 7.5 square root of F prime C. And how much is the highest concrete strength, right, at this point? You're gonna say this is gonna be F prime C, the 4,000, if you're using here 4,000, correct? Just to refresh your memory, how much is the strain here in the top? How much is that strain?
0.003.
Yeah, okay, all right. Okay, very good. How about here? What is that? This gives you the stress in the steel. How can I figure this out? Let's look here at this. Now, based on this stress compatibility analysis that we have done, we're able to figure out epsilon S, correct? If I have epsilon S, what I need to do, which is the strain in the steel, come here to this diagram, draw the strain value at any point, right? So you have the strain value here. You just draw a vertical line because it gave you the strain value. Once it hits this, the stress strain diagram, you go horizontally, you read the stress value, and then use it in here. I said, okay, so this is strain analysis is going to be very important to figure out the stresses in the concrete and the steel and find out the forces and all of that, right? So what is this FS? FS is going to be the stress in the steel at strain of epsilon S, whatever value that you're going to come up with. So you come up here with this one, you're going to be drawing here vertical line, let's say here or here at any point, and once it hits this curve, you go horizontally, you figure out the stress in the steel FS. You say, okay, here's FS. So, okay. How about the forces? Now I need to determine here the internal forces. This is not external forces. External forces means like dead load, life load, some loads that you put on top of the beam. This is now is going to be internal forces. So, okay. How much is the tension in the steel? When you have any steel, you have a stress, uniform stress of Fs, and you have As. Tension force equals to what? As times Fs. Because what does mean by stress? The stress is going to be equal to a force divided by a cross-section area, like normal stress, uniaxial stress. So the tension force equals As times Fs. And with that, I have here the tension force. How about the compression force? You say, oh, now this reminds me with what we have done in the uncracked section. I need to do integration of this shape. What do you mean by integration of this shape? I need to find out the volume of this shape. And the volume of this shape is going to be one compression force. I'm going to call it here C. So C is going to be the compression force on the concrete. But you know what? This is not an easy distribution. It was simple when I have rectangular distribution. I just say here the volume. Whatever stress times this area is going to give you the force. When I have triangular distribution, I said, well, this is kind of tough. I need to find out the volume of this block or this prism. So I'm going to say the stress times this height divided by 2 times the width. And with that, I came up with the force. Now I have this weird shape. And the question is, do I have an equation for this? How can I figure out the volume of this shape or the area below this curve? Is there like an equation for it that maybe I need to do integration? Answer is no. There's no equation. We need to do some approximation because this is actually a tough problem. It's going to be very tough to find out the volume. And even if I'm able here to find the volume, where is the point of application? Where is the centroid of it? There's going to be additional problem that I'm going to be unable to do it, right? This is going to be tough. Find out the force integration, find out the location, the centroid of this shape. This is going to be lots of work. How about this little bit of a tension force, right? Because you have here a tension force, right? You see this tension in concrete? Oh, this is gonna be easy. But now I have lots of forces. I don't like that. This is not design. It's gonna be like research. I don't wanna do this. I'd like just to design the beam. So I'm not gonna be working with this. I need to simplify it. Are you guys here with me? Are we clear why simplification is needed in this analysis?
Yes.
Yes.
So this simplification is needed because the actual stress distribution looks like this parabolic shape, and they have also a little bit of tension. And it's gonna be real tough to find out the volume, which means the force for this shape, parabolic shape. I don't have an equation for it. Also, it's gonna be real tough to find out the centroid, the location of this point load. I don't know how to do it. It's gonna be very complex. Some people would say, let me divide this into slices, like very small strips. Let me find out here tons of forces, like 10 forces. So it's gonna be C1, C2, C3. I'm gonna say, now you remind me with what we have done here in the uncracked section, right? We have 3 forces, C1, C2, and C3. And for each one of them, I need Z1, Z2, Z3. And let's find out the moment capacity this way. I'm gonna say, great, but how would you find out the values for each stress to do the volume? I still don't have an equation for it. So it's gonna be lots of work. So that's why we need to simplify it. Okay, here's simplification. We will have this witness stress block. That was done very long time ago. I'm not talking about the 70s or the 80s. I'm talking about 1800, 1895, I guess, if I'm not mistaken. So in the past, this guy here, he came, he'd like to do concrete design, and he found out it's gonna be really impossible to do the analysis this way. And he wants to simplify it. He said, let me substitute this distribution, the entire thing here, with this stress block. Let me just make it like a rectangle. And he said, the amount of stress value of this rectangle is gonna be equals to 0.85 F prime C. What's F prime C? It's gonna be the stress value, the specified concrete stress that you use, which in our case here, the one that I used as a just numerical example, I say 4,000. So it's gonna be 0.85 of this 4,000. Okay, good. He said, I'm gonna come here with a block depth equals to A. What's the block depth A? He said, I will give you some parameters to figure it out, some simplification here. And he said, depth of the neutral axis, and this is actually the symbol that we're gonna be using start from now, is gonna be called C. C lowercase is different from C uppercase. Usually, if you see the term C uppercase means a force. If you see it lowercase, it means a dimension. Same thing. If you see here the term, let's say T lowercase, it refers to a thickness. If you see it here, T uppercase is going to be a tension force. So he said depth of neutral axis from the compression fibers is going to be equal to C lowercase. See, great, understood. And this A neutral, this is going to be the compression block depth, is going to be equal to A lowercase. And as you see here, it's going to be smaller than C. We said, fine. This is going to be his method. He'd like to simplify it the way he wants. And then he says it's going to be equal to beta 1. We don't know beta 1, but he said, I'm going to give you here some values for beta 1. And I'm going to give you a small graph for it. I said, fine. Anyways, this is going to be A. This is what I care about. It's going to be 0.85 F prime C. Now the question is, how much is the compression force after this simplification? You say compression force is going to be equal to the volume of this block. And how much is that? How can I figure this out? You see, this is simple because now you have the volume of this block. Volume of the block is going to be 0.85 F prime C. It's going to be this stress value times the depth A times the width B. What width B? This width B. So it's going to be like a rectangular block applied here. The stress value perpendicular here to the screen is going to be 0.85 F prime C. The width is going to be B, and the depth is going to be equal to C lowercase, not C uppercase. You see the C lowercase. Do we have this written somewhere here? I'm going to say yes, it's right here. Look at this. C equals the compression force 0.85 F prime C. And instead of saying A, they put beta 1 times C, which means A, right? Times the width B. I said, this is going to be much simpler. Even simpler than the uncracked section to have done. It's going to be just so simple. I like this method. And I know that this tension is going to be the same as the compression, T equals C. And this T is going to be equal to C. This is great, which means Fs times epsilon S is going to be equal to that force. So they made it here much easier for us. Let's look here at the equation at the bottom. As you see here, the equation says C compression force equals, it's going to be exactly the same, 0.85 F prime C, the stress value, times B, the width of the beam now is going to be perpendicular to the screen, times beta 1 times C. What's beta 1 times C? Which means it's depth. Or we can say 0.85 F prime C times B times A. So I can take beta 1 C and replace it with A. And this is going to be the simplification that I'd like to see here in my analysis. Otherwise, the analysis is going to be a hell of a job. It's going to be real tough. I'm going to stop here, but I'd like to hear questions from you. We still have a few minutes.
Could you go over one more time what you meant by the perpendicular force going towards the screen?
Oh, I'm not talking here about perpendicular force toward the screen. I was talking about the width in here. The width is going to be perpendicular to the screen, right? Because this is here the depth. This is going to be the depth of the stress. And this here, you see the stress block here? Here's the section, concrete sections right here. So this stress is applied on it. Let me take you here. This stress distribution applied on the section, in this section here, right? Now, this piece is going to be exposed to compression, and this piece here exposed to tension. So this piece here is going to get compressed this way, and the bottom is going to get into tension. So this, the whole thing here is perpendicular to this. How about the stress? This is stress here applied is going to be on that face, which means it's going to be perpendicular to it. See the stress distribution?
Yes.
Concrete face. So the stress here is going to be on that section, on that face of the concrete. And the stress is going to be perpendicular to it, right? Now let's look here. This stress distribution is going to be perpendicular to that surface. Does it make sense now or no? Still not clear. I'd like to hear from you guys. Is this clear or not really?
Yes, so the simplification part is only for the compression, only for the top part, right? Doesn't include the small tension section.
The small tension in the concrete is gone.
Okay.
This tension in the concrete, this little piece, we don't have it anymore. Look at this. This is now going to be the analysis, right?
You just ignore it, or?
It is included in here.
Okay.
So this here, this block, substitutes this thing, the whole thing. And this force, this C, this is going to be used instead of this tension in the concrete and this C in the concrete. This one force is going to be substituting these two forces. So now you have just one force. So you see the system here is kind of complex a little bit. You have compression in the concrete, tension in the concrete, and the stress distribution is going to be perpendicular to that surface, like what you see here, right? Something like this. But look what happened here. It's going to be only one force as in the compression in the concrete. So the concrete force becomes just one force as compression.
Okay. Thank you.
No problem. All right. If you like to leave, go ahead, sign out, type your name, and leave. If you still have any questions, let me know.
Thank you, Professor.
No problem. Good luck.
Thank you.
Thank you.
I have a homework question because I realized you don't have office hours today.
Office hours was yesterday.
Yeah, last Tuesday.
Okay.
What question was it? I just want to know, one of the homework problems was asking about like normal weight concrete and lightweight concrete.
Yes.
And I was just trying to figure out if my explanation was like a good explanation. Like I just basically said like the difference is like, oh, the unit weight of normal is like 150 PCF and the lightweight concrete is 110 PCF.
You see my
And
screen?
I looked in the book, and I also said about like Cornell University did like kind of like a recommended value for like concrete strength. Is that okay for both of them?
Yeah, because this is here just about the weight, right? And then I give here a section as a comparison when it comes to the allowed by code,
Mm-hmm.
which is the real thing. This give you the code, right? What's the difference between lightweight and normal weight?
Oh, I didn't see that.
Right?
Yeah.
Yeah.
Mm-hmm.
And this is a code. I mean,
Mm-hmm.
the official document.
Oh, okay.
Thing here about this. You see my screen, right?
Yes, I see your screen.
Okay. Any other questions on this?
Mm-hmm. The other one, the plain concrete.
Professor, where can we find like the answer for the second problem, for the County of Orange?
Indicate 2 types of cement.
Is that just based on like the residential like compression, or is it like a specific answer?
You have like type 1 through 5. You could do like 2 and 5, which is more common.
Exactly. You said it right. It's gonna be 2. It's gonna be 5 and 2. So it's gonna be this 2. It's gonna be type 2 and type 5. Do you know the difference between the two? Do you know which one is that we use everywhere? The common one, the cheap one.
Type 2.
It's gonna be 2. Why would you use 5? At what cases?
High silica value, high sulfate residence.
Well, this is gonna be very common, right? Type 5 is okay. We can use it in certain applications. Type 5 usually used when you have some soil issues, you have lots of chlorides in the soil, or let's say that you like to put something close to the ocean.
Yeah, close to the
environment. I'd like the cement to resist the damage, any damage in there.
Excuse me. For the recording of, the link for the records of the classes, have you put it online or not yet?
I will put it, no problem. We have it for other course. I just posted today. So what I'm gonna be doing, just
I mean, for the previous sessions.
Yes. Here's what
have you posted them?
Here's what I'm gonna do, but I want you to be able to find it. So give me a second. Let me explain this to you. Where would you find it? Give me a second. You're gonna go to Canvas, and then you go to list of lectures, and I'm gonna be adding a new one. It's gonna be a link to YouTube list, and over there you're gonna see all the lectures, so you can watch them.
Okay, so on Canvas we're gonna find it. Okay.
Yeah, it's gonna be live. It's gonna be the last line below the lectures. Let me show you how it's gonna look like. This is how you see your Canvas, right?
Yes.
You see the lectures? It's gonna be a line here. I'm gonna be adding it tonight.
Okay.
It just takes time to compile the files because the file is kind of big and I need to press it, change the format, and this kind of things. It's gonna be right here. You click on it, it's gonna open something for you. Let me show you how it's gonna look like. I'm gonna show you another class so that you know and you're not confused about it. Give me a second. So let's say here's another class, right?
Mhm.
So at the bottom, it says here, lectures on YouTube.
Okay.
When you click on it, it's gonna give you something here, right?
Okay.
Don't worry about this. Just click on here.
Okay. Okay.
Don't worry about this. This is something from Canvas. I don't know. But because it thinks that I want to play the videos in here, right?
Mhm.
But once you click on it, it's going to take you to the list. I can show you. Here it is. Here's the list. This for the other class. So it's going to be something very similar to that.
I think Canvas itself has also some sort of platform to you to put it.
Yes, you can put a video, but it's going to be heavy. And I don't want to fill, because I'm going to put all the lectures. It's going to be just too much on this file. And YouTube is free.
Okay. And what about the code ACI? Do we have to buy it or?
You will need it. Maybe you can borrow it from a friend somehow.
Okay.
Or buy it.
Okay.
It's going to be a very good document. If you'd like to be in this business, structural engineering and concrete design, you will need it. If you can borrow it.
Where can we buy any? Is it, for example, for steel, we buy it from the AICS, SSC directly. Is it?
Yes.
What about the concrete? Do we have to buy it?
Maybe from the ACI. You see this?
Oh, okay.
Called the ACI 318. Look first at the library. Because usually order it. If it's gone, you can order it through the ACI and you have the student discount.
Do they have, or do we have to have any promo code or something, or just?
No, you don't need to.
Okay.
But you keep me posted if you need something, or I mean, usually they don't send us anything. They just have it for a student. You provide them like maybe a copy of your ID, school ID, and they give you a discount.
Okay. Okay. Thank you so much.
No problem. All right, guys. Good night.